Good afternoon, everyone. Thank you for being here. My name is Ash Garib. I'm with Co-Architects, and together we'll be presenting our recently finished cancer center in California. So our client is City of Hope. They are one of the top number 10 cancer centers in the nation, and they have this beautiful tradition of really putting the focus on the patients and the patient experience, and that's sort of evident even around the campus and the way that they practice. Our building is located in Duarte. It's a very mountainous sort of a climate with dry and hot, and it has very so this boulder-like rocks. And the concept behind the project is sort of conceptualized as a river carving down the mountain, working its way through the site, and then consequently carving the mass of the building. What's left from that erosion are two masses that house the private functions of the building, and the void in between becomes the public sphere. Here's a view of that with how that all works out. So from the onset of the project, we always conceived the building as being part of Earth. So that was why we wanted to sort of stay with cementitious materials and earthy tones and sort of belonging to that context. So the building is essentially conceived as a jewel sitting on this earthy pedestal of concrete and cementitious materials. And we wanted it to sort of represent those kind of textures of, earth and erosion. So we used board form concrete, board form work with white cement. And this is essentially one of the first walls that we put up in the basement. The project is actually 8 stories tall with a basement at the bottom.
Seeing some of the structural presenters, and I'm not going to go as in depth into the structural design, but there was a lot of architectural concrete, and so the primary focus will be just these 2 walls here. This one, and then the one you'll see in a forthcoming slide. But Ash mentioned the concrete board form and the challenges of a 20-foot tall retaining wall. And so this one here is spanning about 40 feet. So we had to introduce an integral kind of bond beam and traditional retaining wall design. Do one-way design, but in this case we had to do a finite element analysis, find the distribution of it, and as you can see, we had to introduce an element that starts with the S. I think that word is forbidden here, but it's to cut down the span. But yeah, I mean, it's go into more detail on the next wall here.
So for the construction of this wall, a lot of the requirements, the design strength was 5,000. The actual mix, when we got it, the breaks were coming in at 7,000 psi, so we were going above and beyond the straight structural. We used type L white cement, also aggregated 3/8 and sand. We worked on mock-ups to make sure that we were able to achieve that color and the board form look. And then we had to get formwork designed, especially with the radius too. There was a lot of bulkheads, strong backs, shore towers, and especially with that bond beam, it was so congested, we had to hit pockets in order to fit the hose.
So as the patients essentially walk through that public sphere that we showed, there is an area of the building where we carved out, and it's essentially, we call it the sunken garden. So it's a void that kind of connects the exterior and the interior together. And it's also has this sort of a ribbon spiral that kind of wraps itself around the building. Probably.
Yeah. So this here, is a kind of unique design. When you have a large spanning retaining wall, usually, you have to make it really thick and a lot of reinforcement. In this case, we utilize the geometry of the wall itself and not have to introduce intermediate support. So we kind of saw it as a sideways or horizontal truss, or horizontal arc, which we essentially modeled kind of as again, like I mentioned earlier, with the finite element analysis, so that we can make this work without having to introduce any intermediate supports to really achieve the vision of the kind of sunken garden look. So,
Frank, you want to talk?
So I think one of the reasons why we're probably all in this industry is because, we like the friendships that we build on projects. So City of Hope as a cancer research institution has a great story, but also the project team, where people come together early on in the project before you deliver goods and the architectural wall. You're designing and doing structure well in advance of, opening the building. So I love the snow in Aikido, because in California, I don't know if you guys have ever heard about this, but we have atmospheric rivers now. So we used to get a fraction of an inch and it wouldn't rain for 11 and a half months. So this right here, we decided this is a great, the sunken garden, affectionately called. This is where we placed our tower crane. So the Pablo that worked out the structural design for the tower crane. We're about 2 days away from pouring that tower crane foundation, and we got 14 inches of rain in 3 days, which is more than LA gets in an entire year. So we're about this deep in water, and we got to do it again. So I love the backstory, because that's really what makes the project and all these friendships come alive.
You want to talk about how congested all that?
Oh yes, again, this is the sunken garden, affectionately known, but we did all our shoring outside of the garden so we could do this complex geometry, and then this is also where we did our tower crane foundation.
This is essentially the finished product with the board form wall, and you can kind of see the ribbon going around and how the guardrail wraps around it. In addition to the board form walls, we also have sort of a variety of finishes and different ways of going about the concrete. So Andrew, maybe you want to, or Frank, maybe you want to kind of talk about all the mock-ups that we did and the different finishes that we're using.
Yeah, so for our white concrete that we did, the white cement, we essentially went through the similar process. We had multiple meetings, distinguishing features, what's important, how are we going to achieve this, and we can go to the next slide, another example. But if we had prefabricated forms, and we figured out how we have to do that and where we come from. Next slide as well. Same thing, precast benches. Everything was so detailed and so out in front that we had time to make any adjustments and make sure that when we're building it in the field, it matches with the architect's vision and works with structural design. We did a great job with all of them on this by identifying those.
And again, just a little bit behind the scenes, you see all the courtyards and the decorative concrete. We're actually on top of about 4 or 5 feet of high-density concrete, because this is a medical facility. So there's a linear accelerator in the basement that we're shielding all the radiation. So all that needs to be coordinated in advance, because this is actually the basement. It's waterproof, and then there's a lot of modalities for the hospital underneath it.
And we also, did as many mock-ups as we could, trying to get things right. And it always becomes apparent that the first try is a little, it could always use improvement. So having a great team that, is willing to kind of make sure that things are right and not just on schedule or on budget, I think really helps to kind of bring a project of this magnitude together. So thank you all for your attention today. Appreciate you.
we're going to welcome Tracy Lowe, International ICF Specialist with Intraspec. Tracy provided ICF technical and architectural support for the low-rise structure category first place winner, the Altamura residence. He will share how this project achieved a net zero disaster-resistant structure in the presentation. Please welcome Mr. Lowe.
I'm probably just going to do the arrow up and down. Okay.
Sounds good.
Again, my name is Tracy Lowe. I was invited here by the actual architect for the project that's pictured here. His name's Nicholas Nikiforuk. He's been working in ICF for 35 years. And he invited me to come because I live in Columbia. We've been talking about ICF for a decade. Unfortunately, Nicholas had to go in for surgery on Thursday and was unable to attend. So he asked me to come in and kind of get his back. So I just got the information on this yesterday. So hopefully I can work through it. And if I can't answer any of your questions, I can give you Nicholas's contact information, and I'm sure he'll be happy to work through it. I do have some knowledge in the industry, so maybe I can answer it, but if I can't, I would be glad to give you some information. ICF stands for Insulated Concrete Forms. It's basically a piece of styrofoam, a bracket, and another piece of styrofoam that build the wall. You pour concrete in it, and you end up with a wall and roofs. And now you have a complete, what we call cave above ground. So the temperature is always sustainable to the same, doesn't fluctuate much, 4 or 5 degrees, and it makes it a really, won't burn down, won't blow away, storms can't interfere with it. And with some new technology we're coming out in 2026, it's even going to be better. So that's basically the gist of it. This is a front view of the property that was finished with the all concrete and the concrete light pillars there. Another view of the unit with the steps. This is the rear view of the unit. This is the 12-foot wide footings using the ICF forms. The next 3 slides show all of the footings that are being built so they can pour the concrete. And this is actually them pouring the concrete and getting it ready to dry. So there's all the footings. This is the first floor row of footings that were done. This is the placement of the first row of the ICF forms. Again, there's the styrofoam, the brackets that connect them together, and the other piece of styrofoam. And then those black brackets actually are the studs in the wall to mount whatever you want to mount to it, drywall, whatever it might be. So when the wall is finished, you're done. There's no wrapping, there's no insulation. Put your brick or siding on the outside, put your drywall on the inside, and you're done. It makes this process really, really fast. This is the Altamura family. Nicholas is in the bright yellow shirt on the left there, and then that's the owners of the property. And you can see somebody building another wood project that'll burn down the next time they have a fire. Ours won't. This is the first row of forms going in, sorry. This is they're putting in the slab rock to fill it, and then they're doing the same there, and then they'll be compacting it as they go along. These are the forms for the light rails or light pillars they made. And there's the actual concrete light pillars right there. The next 4 slides are of the curved wall that they built. This is really cool with ICF. You can actually do curved walls. So here's one, another one with a little sharper curve. And this is the actual pouring of the concrete into the actual wall structure. This is the second floor of ICF walls going up. And then this is the cantilever balcony right there, which is another innovative thing that Nicholas developed. A lot of people that do ICF walls don't do ICF roofs. Nicholas has been doing them for 5 or 10 years now, and he's invented the whole process of getting that concrete roof done at the same time you're doing the walls. So again, at the end of the day, you end up with a cave above ground. And if you've ever been in a cave, it doesn't make any difference what the temperature is outside. If it's 25 degrees, it's 67 degrees in the cave. If it's 100 degrees, it's 67 degrees in the cave. And it's the same thing with an ICF property. This is the ICF roofs. This is the outdoor roofs getting ready to be poured. And the pillars again. And here's them actually pouring the ICF concrete, or the concrete into the ICF roofs. Another shot of them pouring the upper walls and the roof. Here's a drone shot of the completed roof section. Again, getting ready to pour. That's a completed shot of all the wall structures and roofs, all done and poured. This is the rear steps that they did in concrete. There's a beautiful shot with the rainbow above. It's a pot of gold, they called it. This is an innovative little doggy area they built using the curved ICF. That's the finished dog and the side view of that. This is the start of the ICF stairs. Oops. What did I do? I'm sorry, Denise, I hit something. Just popped up.
Oh, don't worry about that. Just, there you go.
Thank you. And then here's the actual steps. And a beautiful shot of the steps with the lights. This is the rainbow, the curved eyebrow they call it. This is the double dormer in the front area. Same thing there. This is a shot of the living room. Living room showing into the kitchen. Pretty nice windows there. Again, the living room, and then the living room into the kitchen. The actual kitchen with the archway. Another shot of that. And then the actual kitchen again with that archway. This is the dining room. Check out that wall mirror. And then the dining room with the lighting. This is the guest bedroom. I could live there. This is the hall bath, guest bath, and the master bath with a walk-in shower. Got to have a gym. And then the music studio. This is the framing of the double-sided fireplace. And then the finished fireplace. And then the double-sided, the master bedroom fireplace. And then the finished fireplace. And this is IntegraSpec's demo they do at all the World of Concrete shows and builder shows that they do. So that's it. Any questions? I'm in the Maryland area. I live in Columbia, and we're actually promoting ICF in this market. It's becoming a more popular way to build houses, especially since people are pushing net zero and want a nice, quiet home. So if you ever need to reach out to me, I'll give you one of my cards, and we can talk about how that might happen. And we are looking for builders and people that want to learn this technology. Thank you so much.
Good, thank you, Tracy. All right, our next presenter, Lianjin Bao, Chief Structural Engineer at East China Architectural Design and Research Institute Company, Ltd. He will discuss the structural design and construction of the Chinese fan in the Shanghai Grand Opera House, an architectural landmark inspired by the open fan along the BS and MS degree in civil engineering from National Taiwan University and is a licensed professional engineer. Min Yu has repeatedly earned Taiwan's highest national honors for quality, safety, and sustainability. In 2025, as general contractor for the National Taiwan University's Humanities Hall, he received Taiwan's first ACI Excellent Construction Award, underscoring Chairman Chia's engineering rigor, sustainability, innovation, and global vision. We will be presenting on the mid-rise structures category second place winner, National Taiwan University Humanities Hall. Please join me in welcoming.
Good afternoon, ACI members and friends. Congratulations to all the winners. Mr. Price, thank you for your help. Mr. Rusty, thank you. Yeah. Fengyu is a construction company from Taiwan. Now that's me present at National Taiwan Humanity Hall on how to boost concrete performance. There are 23 million people in Taiwan with 2 cubic meter of concrete consumed per capita each year. Concrete technology and its applications are well developed in Taiwan. Taiwan ranks 22nd among global economies in terms of GPT, with 70% international market share in wire foundry. As a high seismic region, Taiwan relies on high performance concrete to support both semiconductor industry and the everyday infrastructure. TCI has been leading the advancement of concrete technology in Taiwan, with a focus on decarbonization and circularity. It's an honor that two Taiwan projects won ACI Excellence in Concrete Construction Awards in 2025. National Taiwan University Humanities Hall stands as an emblem alongside its iconic heritage main gate, College of Liberal Arts, and the Royal Palm Boulevard. Concrete interprets the existing courtyard house, forming modern quadrangle that bridge heritage, campus, and the city. The 50-meter steel truss, supported by monumental concrete columns, span over the second courtyard, offering an unobstructed view of historical architecture. Concrete shear walls enhance the hall's seismic performance by 50%. The steel truss is filled with high flows, self-compacting concrete to improve fire resistance, corrosion protection, durability, and seismic performance. To control cracking, we adopt a 4-stage concrete mix design, refined by on-site markup to finalize the optimal mixture. By integrating BIM technology, the entire structure was deployed into 117 concrete pouring units. For the 50-meter-long steel truss, a post-cast segment method was used 3 main segments were cast, each cured for 28 days before placing of 60 cm wide post-case tree. This released 28% of the concrete shrinkage trace, effectively preventing crack. Various architectural details show the workability and the versatility of concrete. National Taiwan University Humanities Hall is shaped fair-face concrete cast with cedar formwork. The natural grain, animated by light and shadow, convey a quite wide resonance with the building's humanistic spirit and bridge the dialogue between past and present. Sustainability strategies, low water cement ratio to reduce cement content, dredge river aggregate to reduce coin, 30% cement replacement with GGBS, fair-face concrete as a final finish to eliminate secondary surface treatments, precast UHPC sunshade to reduce thermal load. Thank you, Taiwan team member. Stand up, please. Yeah. So, give a biggest, give a hand. Thank you. But I have a video. See. Yeah. Video is okay.
National Taiwan University Humanities Hall is surrounded by a century-old historical campus. Concrete reinterprets the former courtyard house, forming a modern quadrangle that bridges heritage, campus, and city. The 50-meter sky bridge, supported by monumental concrete volume, spans over the sunken courtyard, offering an unobstructed view of historic architecture. Concrete shear walls doubles the structure's seismic resistance. Steel frameworks of the sky bridge are enhanced with HPC, ensuring fire resistance and corrosion protection. No coatings, no additional finishes. SCC is cast with cedar frameworks that imprint the surfaces with wood grain for a soft and warm appearance. Mock-ups and testings are done to evaluate and refine the mixture, techniques, and aesthetics, while BIM assists in achieving accurate execution. Various architectural details show the workability and versatility of concrete. Sustainability begins with how we mix the concrete. Dredged river aggregate replaces quarried stones. Slag instead of cement, reducing carbon emissions by 2 million kilograms. A low water binder ratio enhances durability and serviceability. Precast UHPC sunshades at 3 angles efficiently lower heat loads. Each concrete pour is a firm commitment. No haste, no compromise in concrete and in the human spirit. Fengyu Group.
Today is my birthday. My first time in the United States. It's my honor to stay here and give a presentation. Thank you.
Happy birthday to you. Happy birthday. Happy birthday to you.
Good birthday, Mom. All right. So in our next presentation, we'll welcome Wei Liang, project manager for the T3 project at Taiwan Toyon International Airport and assistant vice president at CPCI. They'll present on the apron project covering 420,000 square meters at Toyon International Airport, the second place winner in the plaza. Please join me in welcoming Mr. Yang.
Hello, everyone. My name is David Lin. I'm very happy to represent Taoyuan International Airport Corporation to introduce everyone this mega project. As you know, in this year we win the award is about apron and taxiway. It's one of the tender package of this mega project. Total, we got 25 tender package for whole project and plan. So I joined this project since from 15 years ago. Willie is 12 years ago. So we worked together a long time enough. So, in organization with this slide, TYLIN, WSP, and NACO will be the planner and the project management team. And CCI, Rachel Rogers, ARAP, and the FCA is design and supervisor team. And for TP3 is this apron project. BES is the contractor which build the apron and taxiway pavement. Okay, I will hand over my microphone to Willie, and he will keep going for technical presentation.
Okay. Before the presentation, I would like to thank to ACI for giving this opportunity for us to learn a lot, so many great concrete projects from all over the world. Okay. My name is Willie Young, project manager for design and supervision consult of from the three projects in Taiwan Taoyuan International Airport. It's a huge project area, and also it is demanding for us. We are so proud of our achievement, not only for the huge area, but also the work involves so much detail and require a lot of monitoring, coordination, and we did it without any interrupting the airport operation. Yeah. Here's the contents of the presentation. This airport construction located in Taiwan main gateway, Taoyuan International Airport. This airport is the number 30 business airport in the world for handling of passengers. Currently, new mega terminal is being built to accommodate the future growth and air traffic in Taoyuan Airport. And this project is going to provide additional apron and the taxiway to provide 27 new contact stands. Therefore, the content of this project includes the surface area of 42 hectares of rigid pavement, 30,000 concrete slabs. Each slab is around 5 by 5 meters. And also the volume of the fractured concrete is 165,000 cubic meters. Structured concrete, 94,000 let me introduce the future of this project with some slides. Optimal design. We adopt the FAA standards for determining the pavement thickness and to accommodate the various types of aircraft and the volume of operation. Then the PCC surface layer has a bending strength 700 psi and 46 centimeters thickness. The layer below the surface layer is cement treatment grade bottom layer. Thickness is 30 centimeters. These are all the design to improve the durability and resistance to water damage. The second feature, saving on cost and reducing carbon emission. The total volume of concrete in this project is around 260,000 cubic meters, and a considerable amount, that's 48,000 tons of cement is replaced with reusable resources like pozzolanic material, which can improve the constructability and the durability. And overall, we also reduce the carbon emission by 16,700 tons of carbon dioxide. Okay, that's the material. The second feature, applying special tools and the technology. We developed a testing machine to conduct a heavy-duty vehicle test of the pavement. This is based on the FAA's spec. For the large area in April, we also adopt a leader technology to apply the ground data and the analysis to confirm the flatness of the entire area, April area. It's an efficient and comprehensive way to do that for inspecting large area. Precise measurement and control. We constructed 30,000 slabs in a meticulous way, which includes using steel molds. This steel molds and set the elevation of four corners of each slab. Therefore, we can control the overall slope for drainage. Soil cutting and pouring is also performed with precise steps on site to control cracking. This is some figure here. In order answering, besides the precision, in order answering the specific high condition in every area, we apply the curing agent to create a tough and durable water retaining layer to slow down the water loss. It's an effective way to ensure the quality of pavement. Okay, here is a short video to show the critical water at the site. This is the heavy vehicle testing. And the leader technology to be used to confirm the flatness of the apron. 5x5 slab. Put the steel mold to, and this over all this data is a design data. Therefore, we can have the overall flat area, down bar, and tiny bar. This is the PCC pouring. The paving and the levee. Sweeping with cutting. With the elastic. Okay. Then let's quickly go through some features of this project. Okay, we have a rich pavement in huge area that's 42 hectares. And we complete the additional parking gates that 27 to provide more capacity for the growth traffic. 13,000 concrete steps skillfully joined together without defects. And superimposed pavement structure that to increase the strength and improve the durability. Fire service for aircraft movement and drainage that results from the meticulous construction way for the stack. Huge volume of concrete to accommodate the different loading from the different, because we do have the focus the different flights in the future. Then we know, because the loading is so heavy for the aircraft and only such small area, then the loading is totally different from the vehicle. Yeah. Okay, we also have 220 earthwork to reserve for the other projects, the environmental way to do it. Okay, besides the good condition of the effort, there is something more exciting on the way, because the condos, the terminal building is going to open in the coming future. Yes, and we Taiwan is eager to show its fantastic achievement at that time. That's my presentation. Thank you.
Any questions for Lavey or Willie?
Willie.
That was just the apron area, right? That was not any runways?
No, taxiway also included. Taxiway, not no runway.
Okay.
Yeah.
Thank you.
And it looks like we have the winning project for next year. I hope.
First place.
Good luck.
Yeah.
Very good. Very good.
Thank you.
Thank you so much.
Yeah. Thank you.
After 3 years, 4 years.
I appreciate that. All right. Our final presentation today. Joe Fursley, professional engineer, structural engineering, senior principal at CKC Structural Engineers. Joe is also a voting member for numerous committees and associate member for the joint ACI, ASC, and Research Practice Committee. Joe will present on top of the mayor, meeting the challenges of tall building design, which won second place in the high-rise construction category. Please welcome Joe.
Well, thank you, Rusty and Denisha, for putting this whole thing. And I would like to extend my thanks to the entire ACI staff that put that ACI Excellence Award program together. It's humbling and gratifying to be part of it. We started placing our project in this program since the inception. We already won 4 times high-rise category, second place, yet to win the first place. But it's great thing about this award is actually an international award. When you come to these presentations, as we can see here, you have people from all over the world bringing these beautiful projects. As we saw last night, all these entries were amazing and a lot of hard work. Every project is touched by 1,000 people or more by the time you design it, construct it, build it, and it changes the landscape of cities, for that matter, and touch us in so many ways. So the air is a long history. It's in Seattle. If people don't know, Seattle is a high seismic region. There's a subduction plate moving. A lot of attention is given to earthquakes. High-rise buildings are particularly complex structure to design in high seismic areas. The area in particular is a 45-story tower, 5 levels below grade, multifamily high-end luxury condominium in the Denny Triangle, which is kind of ties in downtown. It's a vibrant neighborhood of Seattle that ties in downtown with South Lake Union, if you guys have been to Seattle. And we had to pay critical attention to cost. It's a private-driven project, and to speed, because schedule, cost, all these things come together to make these projects happen. So just a quick overview. It's 454 units. It's about 600,000 square feet, 6 levels below grade, and of parking, and then 3 levels above grade was parking. Beautiful lobby area was amenity that ties in the corner of that street. Many thanks to the developer Holland Partner Group. The good thing about them, they're also the general contractor. Holland Construction will also thank the concrete contractor, which is Conco Concrete, and Robert Thompson was the architect. If you could see, look at the building, the way it's been designed, it actually was inspired by the Pacific Northwest, where you have these jagged sides. This is actually the tectonic plates, quote unquote, per the architect, that kind of shows that facade that goes in and out, which created some challenges for us on a structural standpoint, because we had to create these long cantilevers without moving columns. Quick thing on the structural overview of the building, has a lot of great things and innovations and buildable details throughout. So we use 8-inch post-tension slabs. We have spans about 29 to 30 feet and cantilevers up to 12 feet without any drop heads. We use high-strength column up to 15,000 PSI. That was a bit challenging because the entire building will also use one of the first buildings that used Type 1L cement in the U.S. of that size to reduce carbon footprint. We're also on the walls, so the lateral system of the building is actually not allowed by the prescriptive language of the code, so we have to do performance-based design. So we have to analyze the building with this core, and we'll put fiber link beam that are not part of the code, but you can do it if you do nonlinear analysis and show that the performance of that core would work nicely. It takes a lot of energy. You put 11 pairs of ground motion. Each one is about a minute long, and every 0.05 seconds, you check the stresses on the building as the 11 pairs moves that model. So it takes a lot of iteration, a lot of back and forth. One of the things we wanted to do is, we had 16 columns. We worked hard and fought hard and negotiated location with the architect and the ownership, so we don't have to add any transfer beams. Buildings this size, a transfer beam would be a floor height, and would slow down construction and would disrupt the behavior of the lateral system. So here's a model. This is out of Revit, which is Visicon 2, but you can see here, the middle, the red is the core, going concentric core from the foundations, the foundation mat, all the way to the roof. You have 16 columns around. We created some crafty, you can see here, jogging and walking of columns. Some of them walked in 3 different directions, just so that we don't put any transfer beams. So we didn't have any transfer beams at all from dynamic base. We call it dynamic base, which is grade level all the way to the top, which made the things much easier, less congestion, and eliminated all the transfer beam that could impair some of the occupancy of floors. One of the cool things we did, and this is supposed to be a video, maybe the next click should do it, is because we had a high strength, you can see here, this is the column, and the column was 15,000 PSI concrete, and the slab was 6,000 PSI concrete. So we don't have, the code requires you to do puddling. I don't know if you guys know puddling. You basically take another mix of concrete, you put it on top of the column, intermix, and then, because you don't have so much differential between the slab mix and the column mix, at the column slab sandwich, which is right here. I'm going to click to see if that video will work. Oh, yeah, it does. So these are the stud rails. This is a rebar. And the way we do that, these are the shear bars that we put into this. The green is the PT cables. You can see them here too. And then this is a top reinforcement. And then you put this stay form. And then when they pour the slab and they stress it, you have this little hole because that stay form keeps the core of the column without being poured. But it does not slow construction because you pour the slab, you stress, you have this little cavity over the column. The next day they come and pour the column, and the concrete mix of the column goes into that cavity. It's pretty cool, slick trick. I'm gonna replay it again, see if that works. So you can see it again, and then avoids the puddling. The trick was usually to put the stay foam, but what they did here, they put that stay foam first. You have to make sure you put the shear steel bars so that on top of the friction between the concrete, you have shear steel that passes through. It's like a midpoint bar that goes into that joint. And then they put stay foam again up here after they put the top bars, and they pour it. Much easier than putting two mixes, try to intermix them, so on and so forth. So that was a big thing on constructability and buildability. The other cool thing on that job is we used actually fibers link beam. High dosage of fiber, you could see it, and instead of using the diagonal reinforcement in these beams because they are taxed by a lot of shear, and a regular beam does not work. So what we did here, we put basically that piece of concrete between the two walls. So this is a boundary element of the wall, and this is the other boundary. Between the two walls, we put a special mix with high fibers. It's about 160 pounds of fiber per cubic yard. It's a very healthy fiber dosage, to 200, depending what we need. But what happens is you reduce the rebar in that beam by about 40% from a typical beam. So it's much easier to place. You don't have the diagonal that clashes with the top rebar coming down. So it turns out to be a very constructible tool that streamlines the rebar of the core going up the building. And the neat thing about it, a lot of times you can pour this after the fact. What they do is they pump the wall with concrete, they bucket this with a steep bucket with fiber concrete, they vibrate it, and they put stay foam, and they keep on going with the building. Here's a video showing how that fiber concrete is putting in. It's interesting, we use the SCC mix. When you put the fibers, not because the fibers suck, steel fibers, they don't suck water, but it turns the SCC mix to a 6-inch slump. You have a 27-inch slump for a self-consolidated mix, and you put these fibers in, suddenly you're down to 6 inches, plus or minus. So, but they all over the mix, you don't see them when you strip, so it's a pretty neat thing. We've done about 15 buildings like this throughout. Now, the underground, the below-grade construction was really interesting. First of all, we started with a mat. We had a lot of cool concrete specification for different concrete mixes for the building, but the mat is basically about 10 feet thick to plus 10. Around the elevator pit is about 15, but basically most of it is about 10 foot thick. And they did a single pour for the entire mat, about 5,000 yards. So basically, they start at night, they finish in the morning, about 12, 14-hour pour. You have trucks coming in. So think about it, 10 feet of concrete, it's mass concrete. There's a high heat of hydration, so we always make sure that the cement content of these mixes is less than 450 pounds, and we kind of extend the strengths, so you don't need that strength till about 90 days or 120 days to make it easy on the ready-mix guys to bring those mixes to us. If you pour that mix like a regular 6,000 mix with 600-pound cement, you won't be able to walk on it in 2 days. It's going to be very hot. So that's one. Two is we cover it so we keep the heat differential the same between the center and the top of the mat for a few days till things come down. We'll look at the temperature gauges for that. The other cool thing is it's a pencil tower in the downtown, so it's 120 feet by 100 plus feet, 110 feet. So you want to go fast, and the basement wall creates a trouble because if you have to pour the basement wall, pour the slab, pour the core, you'll be stuck in that hole 6 levels below grade for several months. One job we did, they were in the hole, they came to go down and up, took them a year. So what we do is this is actually the shoring system, that's not concrete. We allow them to put the slabs against the shoring system, And then what they do is they detension, there's tiebacks on the shoring system, they detention it. Now the slab becomes bracing the shoring system, not the tiebacks, so you don't have to do blockouts in the basement wall. And then you don't do the basement wall till later. So these are formwork put at the joint of the basement walls. You have a basement wall above, basement wall below, slab in. And what they do is they come back later when the tower is up to level 2, they come back and shoot with shotcrete the basement walls. And they're pretty thick basement walls, 16 inches. And then, so embodied carbon was an interesting thing on this. Let me just go back here too. One of the things we used is we used a grade 80 steel throughout the foundation, grade 80 steel throughout the boundary elements of the core walls because there's a lot of tension involved. And then we used the confining steel, was grade 80 steel to reduce the amount of confinement. The other thing we did is we created these column cages, 2 lifts, so you reduce the amount of times you put these columns on site. So that if you have 16 columns, what they did, they staggered the columns. It's a cage that goes 2 levels. So some of the columns, you only have to place half of the column every cycle of floors because the other one's already sticking up. You do it the next one. So it's 2-story lifts. And that works really nicely and speeds up the floor cycles by quite a bit on the typical floors above in the building. The carbon was interesting because by just using Type 1L cement, we were able to reduce about 10%. So this is about equivalent, we did the math on it, about 450 tons of CO2 reduced just right off the bat. And then being efficient and putting transfer beam and all that stuff, people don't realize a lot of the carbon reduction is the big question, and I always ask myself, it's like, you see all these highways, a lot of these bridges, but you can easily reduce carbon by making your design a bit more efficient by at least 10%. You always can make your design a bit efficient. So that was a big thing, and then so high strength bars also reduce the embodied carbon. Now, depending how steel is being made, either from iron ore or recycled steel, most of the stuff we use in the Northwest is recyclable steel, so there isn't a lot of CO2, but there's still some because you have to heat it, melt it, and transport it. So by using high-strength steel, you reduce the amount of rebar you use, and then therefore that helps with the carbon footprint. So the project here did it great. We won a couple of years ago the NAIOP High-Rise Residential Development of the Year in 2024. Last week, we won the NCSCA, which is the National Council of Structural Engineering Associates. It was a summit in New York. We won the Outstanding Multifamily High-Rise Project category for 2025, and a few other awards and publications. And then CRSI Award right here in 2024. And yesterday, we won the ACI Excellence Award, 2nd place, but we're working on the 1st place. And so basically, conclusions, we are advancing material. We use innovative material like fiber link beams, fiber and concrete, leading edge constructability. I showed you that detail. And all of it happened was a collaboration with the concrete subs and the ready-mix guys. We sit down with them early on, and we try to make them comfortable with the ready mixes. Otherwise, they get freaked out when they see a 15,000 PSI mix. And I think that's it. Any questions?
15,000 PSI with 1 ounce of that. Any questions for Joe?
Yeah, we did quite a bit of mock-ups early on. We used the first mix. I mean, this is not the first building we used fiber, but we reduced the fiber here a little bit different. But you have to do mock-ups. And what we found out, if they use the SCC mix, you add the fibers in it. The key is how intermix the fibers. You have to do them in the plant early on. You have to talk, because the ready-mix guys don't like to put other stuff than what they have in the concrete when there, but the fibers have to be intermixed so they disperse quite nicely. So we have a lot of specs on that and how to deal with it because we did a bunch of samples on that.
Very good. Thank you, Joe.
Thank you.
Congratulations. Yep. All right, I want to thank everyone for attending and celebrating the winners here. We hope you enjoyed taking a closer look at these remarkable concrete projects. Again, if you missed any of the projects, be sure to watch the videos on the ACI Excellence website. Those are all posted. And if any of our speakers have a few more minutes to invite them to answer questions after the session, again, I want to thank everyone for attending and again, celebrating all these great projects from around the world. Thank you so much. Denise has got